Nothing? All right. That's
Yes,
either
sir.
good or a very bad sign. So let's
Yes,
move
sir.
on.
There's a question, sir. I'm just trying to see what we could formulate it in terms of static load. Sir, I can't remember what I was asking. But there is something important that I wanted to ask from last week, but I just...
Excuse me, sir. Can you repeat what you went through thus far, please and thanks?
It's all in the schedule, Mr. Green. The schedule is in Schoology. You can refer to that. It's all there. All right. So I gave you a reading assignment to look at transmission lines. We had given some basic definitions in terms of these lines. We spoke about them in terms of the nomenclature that is applied. We talked about the representation. Today we're just gonna focus a little on long lines, and by extension that will treat with the transient behavior on lines. We are going to be looking primarily at switching transients. All right, and we'll speak about that in a few. I hope you're hearing me clearly because the rain just started. It's a little loud in here. I hope you're hearing me clearly, but I'll try to speak as loudly as possible. So if you look at the Schoology page, if you're able to access the Schoology page while we are going through the lecture, I've actually put some of these notes, put the notes on transients there. I've also included some of the diagrams that we'll be looking at this afternoon in the reading material section. All right. So if you go to reading materials in Schoology, you will see that listed. So some of the diagrams, maybe a bit much to be drawing. And so I have put them together and included them in the Schoology page. All right, so let's proceed. Okay, so we're talking about transients. But before we get there, we want to look at I suppose Les Brown knew that you were going to do electrical power system, so he just provided you with the best quote he could find. All right. I think this says it all. Anyway, coming from your networks too, we got a classic definition of what a transient is. Yes? And we talk about transients, it's the period between initiation of an action and us reaching steady state. This is true whether we are dealing with electronic circuits, whether we are dealing with systems, and most definitely in the power system, we also have to deal with these transients. And in terms of operations, from an operational standpoint, you will have to be cognizant of these transients that will ensure that your protection system in particular will not operate when, during that transient period. The protection system would recognize it as a transient and therefore will not see it as a fault and trip. Okay? So all of that is built into the power system. We say here that it primarily focuses on design, but outside of system design, you as the person on the ground, that's whether from an operational standpoint or from a control standpoint, need to appreciate transients within the power system. So, treating with this, it gives us clarity in terms of control of, as we have here, transient over voltages or, flashovers, which again, because it's coming from, let's call it a natural consequence of the operation of the power system, we have to militate against that. Okay? We have not gotten into protection, but one of the things or one of the principles that you need to appreciate with an electrical power system is that we want to ensure that we reduce interruptions to a minimum. Ideally, you don't want an interruption because you can appreciate, even with the little floods we had recently, but those who may have been impacted by power outages, it is very difficult today to live in this so-called third world country without electricity. If you think about it, almost everything that you do involves electricity these days. I was sharing with a group some years ago that even though we are using gas stoves, the gas stove also depends on electricity. Today, without the internet, we feel like fish out of water. So reducing interruptions is something that must be high on the priority list for a utility. And so appreciating things like transients is important. Just to give you an idea of of a transient occurring on your power system. You may have had a power cut in your area, and when the power is restored, let us say you were just too lazy to turn off the bulbs in the house. You would see the bulb flash, and then it returns. All of that comes from the transient phenomenon that is experienced in the power network. Of course, might just get a small flash, but if the system isn't properly designed, the result can be much, much worse. So we want to, consider all of these operations. The other thing I would quickly mention at the outset, just to contextualize a lot of what we'll be looking at. We spoke earlier in the module about lines versus cables, and we looked at the fact that one had inductance, which was, relatively speaking, inductance which was higher than the capacitance, while the other had higher capacitance relative to the inductance. And these characteristics will impact how the current travels through these different media. So we're going to be, looking at all of that. When I connect the two, how does that impact the operation of the system? So, at some point in New Kingston, we have to come from below ground. We have to come from the cable and connect it to an overhead line. Does that make a difference? We have to discuss that. We have to look at that. So there's an interface between a line and a cable. Is there a difference? All right. So with that said, let us get into what we need to talk about. So from your reading assignment and from what we have discussed before, we spoke about short lines. And the representation here with your resistor and your inductor is a short line representation. And from what we have done, whether in networks 1 or 2, the understanding is that with a voltage at the input, if we should energize this line, we are expecting an output instantaneously. That's our understanding. We were not thinking of any delays in this line. Similarly, for your medium line, your pi representation, where you have your admittance over 2, and of course these parameters have their importance. Just a minute. All right. Yeah, these parameters would have been explored in lab number 1, where you looked at the impact of changing these parameters on the operation of your power system. Yes? All right. Now, as we said, for both these circuits, we are dealing with lump parameters. Yes? And we know what lump parameters are. And that just helps us with easy analysis. However, from a practical standpoint, each unit length of the line is considered to have a small value of resistance, capacitance, or inductance, which contributes to what we represent as a lump parameter value. Right? So the resistance, the inductance, capacitance are really given on a per unit length basis. Okay? And then distributed over the length of the conductor. So what you have, or what you would have, is your resistance per meter, but then you have 100 kilometers. And so that resistance per meter is distributed along the entire line. Right? Similarly, your capacitance, farad per meter, your inductance, Henry per meter, distributed along the entire line. The assumption is that with your constant cross-sectional area and the constant space between the conductors, that these parameters are uniformly distributed over the entire length. All right? And so we represent that as shown. And note you have R prime, L prime, and C prime. These represent resistance, inductance, and capacitance per unit length. All right? So those are your distributed parameters. Are we finished with that?
No, sir.
All right.
All right, finish, sir.
Okay. So the question is, how do these distributed parameters help us in terms of analyzing what happens when we energize a power line? All right? And that's what we're going to be focusing on this afternoon. So we're dealing with steady state analysis. When long parameters are convenient. So if I have the absolute resistance, inductance, etc., that's fine. However, when we're considering transients, then we need to consider the distributed parameters, or we need to use the distributed parameters. Simply put, if and I've been saying it, you know, I've said it a couple of times since we got started. If you have a voltage which is suddenly applied at one end of the first figure, that's the RL circuit. If you were to energize it, you expect that the receiving end voltage would appear immediately. Yes? However, this does not happen in the real world, right? There is a delay, and we're going to be looking at how is that delay created, and how do we assess or determine how long it will take for signals to get to the receiving end. All right. So there will be that delay. I energize, so I'm at the sending end. I energize. It's going to take me a time t. I will determine what that t is. It will take me a time t for the signal to get to the receiving end. All right? And we're going to therefore use certain characteristics of the wave, of the line, which in practice results in wave-like behavior to determine what happens at the end of the transmission line. Right. And as we said before, we can only do this using our distributed parameters. And that's what we are going to be focusing on this afternoon. All right, so let's get cracking.
Sir, good evening. By use of wave propagation, are you talking like if the wires are like twisted pair and all of that and stuff?
Okay.
Will affect. In terms of the wave propagation that you're about to express, are you talking about whether the wires are twisted pair or anything like that? It will be seen differently at the other end due to the delay.
What we're simply saying is that when I energize the line, when I energize the power line, because of the characteristics of the power line, that voltage, instead of it instantaneously appearing at the receiving end, it will behave like a wave.
Okay.
Yes. Now we know what waves are. We have looked at waves from A-level physics, so we know that a wave, as it travels along, if it meets up another medium, so it moves from one medium to the next, you're going to have a number of things happening. You're going to have it refracting, you're going to have it reflecting, Again, because it's a wave, it means that when you create that disturbance at one point, the result will not be seen at the other point immediately because it's a wave. So there would be a time, right? So all of those characteristics of a wave, displacement, time, all of that will come into in energizing the line. That's what we're saying.
Okay, thanks. That's understood.
Oops. All right. So while you draw this, let's just, identify a couple of things. So Z and Y, right, are the impedance and admittance per unit length. So Z and Y are the impedance and admittance per unit length. Therefore, all right, let me just let me know when if therefore, the impedance, which we're representing as the series element, Z times an elemental portion of X, right? So this just means the change of X over a particular length, right? So the bit of X, delta X. If I multiply the impedance per unit length by the length, right, the change in length, then I'll get the impedance. Nothing magical about that. The same is true for the admittance per unit length over the same elemental section, yes, delta X, then I'll have an admittance. So with that said, we go now to our sending end. So I connect a voltage Vs, and it results in a current Is. All right? So we have here I, all right? But with this parallel component, and we know about parallel circuits, I'm going to have a current flowing through that. Yes? It means, therefore, using Kirchhoff's current law, the resultant current will continue along the series element. So if the current that goes through the admittance as a result of that parallel connection is delta I, then what will continue is I minus delta I. All right? Beyond that point, obviously I'm gonna have a voltage drop across this element. Yes, which means that I'll have a voltage other than V across the next portion. Again, another series, and then I'll have another voltage drop. Yes, I have another voltage drop here. So I'll get a lower voltage. So in essence, what we are saying is that the sending end voltage will be slightly different from the receiving end voltage, right? And current. Because you will have voltage drops along the line. And of course, you'll have these small currents passing through the capacitance, okay? We're not gonna concern ourselves too much about the magnitude of those currents and voltages. What I want us to focus on are the principles or the applicable principles that we'll be addressing. So based on what we have here, as I said, you would have delta I flowing through Y delta X, and then you would have I minus delta I through Z delta X. Now, the portion of the line that we are considering is very small, delta X. So if I'm dealing with a small current, all right, so if I have a small value multiplied by a small value, so if I have a fractional value multiplied by another fractional value, it means that the resultant is even smaller than either. So delta X times delta I would tend towards 0. Again, nothing fancy about that. That's basic math. Therefore, for our first equation, we know that delta I, that is the current going through the admittance, would be equal to V times Y, voltage times admittance. Again, nothing fancy. And also, with the impedance portion, delta V would be equal to I times Z delta X. Because remember, the delta I, delta X was tending to 0. So that delta I times Z delta X would be equal to 0. And then, of course, we apply some basic mathematical principles within the limit where delta X tends to dx, then delta V, yes, which is equal to Iz delta X. Delta V over delta X as it tends towards dV dx will be equal to Iz. So dV dx is equal to Iz. We then do a similar analysis for the current expression. I'll get di dx to be equal to Vy. All right. Well, I'm shouting here, boy. I hope you can all hear me. Anyway. Okay. So we make substitution. So d dx. Right? So we're differentiating. So d dx of dv dx would give us di dx times z. But of course, we already know what di dx is equal to. Yes? Di dx from our second equation is equal to Vy. So it means therefore that d dx of dv dx second differential will be equal to zyv. Which I think we can all agree. We can all agree. It's a simple second order differential equation. Second order differential equation. solution of which would be in the form so the solution of our differential equation for V will be PE to the gamma X plus QE to the minus gamma X. Of course, this is something that you would have looked at in math. You'd have also touched a bit of it in networks too, yes?
You said that's lambda, sir?
So P and Q are constants which are found by considering the conditions at the end of the line. Simply put, what we are saying is that P and Q will be based on the boundary conditions. So we know that our solution is in this form. So I suppose now I can confess with it raining like this, I'm really not in the mood to teach, but let us press along, yeah? All right. So the solution, dv dx, yes? We take the second differential, we get gamma squared dE gamma x plus gamma squared QE minus gamma squared. But of course, all of this, yes, is equal to V. So in other words, D2y, or sorry, D2V dx squared, yes, which is what we have here, is equal to gamma squared V. So simplifying, all right, we'll get gamma squared to be equal to ZY. All right. So gamma squared is equal to ZY, which is what we have there, which means that gamma is equal to ZY, and gamma is known as the phase of propagation constant. So we'll come back to gamma in a few minutes. What I want, however, to go on to is to look so we have done the analysis from the voltage standpoint. We want to do it, so to speak, from the current standpoint. Now remember we said that di dx was equal to YV. So ddx of didx, or the second differential of I with respect to x, will give us y times dv dx. But earlier, we had an expression for dv dx, right? Which was the PE to the gamma minus QE gamma. So we make that substitution. So when we make those substitutions, we get I to be equal to y over z e to the gamma x minus QE to the gamma x. All right. So if gamma is equal to square root of zy, we just prove that. Yeah, so we make the substitution here. All right. And the ddx of didx, which we indicated earlier, was equal to zy, which is what we have here. All right, so it's just a double substitution we're making. No, we make that substitution and then we are going to substitute for gamma. All right. So when I put the z within the square root sign, it becomes z squared. Which indicates that we know that this is from our voltage expression, yeah? Which means, therefore, that y over z, the square root of y over z, would be an admittance, or y over z0. And I think everybody in this room will be familiar with Z0. It's the same Z0 you know from networks too, nothing different.
So, sir, what is the relation?
Go again?
What is the relation?
Not sure I understand the question you're asking.
You said that the Z0 in network suite was characteristic impedance, and that was being seen as a symmetrical network?
We're coming to that right now. So I'm saying Z0 is your characteristic impedance, but when we talk about when we in power systems, we refer to that as your surge impedance. Now, you made a point about symmetry. Earlier, we said that the resistance, inductance, etc., were uniformly distributed along the line, which means, therefore, that whichever direction you're looking at, you'll be seeing the same distribution, no?
Anybody else here?
I'm
Oh, no.
over here.
Oh,
I think they all left me, but then again, that's a possibility, right? So will be. All right.
sorry.
Still there, still there.
Yeah, we're there, sir.
All right. So the phase of propagation constant, that's gamma, right? And it's given by alpha plus J beta. Okay? So I'm sorry, I got distracted, which is why I had to stop speaking. So the phase of propagation constant, gamma, yes? We spoke a lot about that just now, right? Is equal to alpha plus J beta. So I'm introducing some new things now. So alpha is known as the attenuation. That one I'm sure sounds familiar. And beta is known as the phase change. So I'm just going to play around with what we have here. So beta is in rads per unit length. Alpha, of course, in amperes per unit length. But for our purposes, we're going to make the assumption that our line is lossless. In other words, there's no attenuation. Right? Now we understand the difference between attenuation and resistance. All right? So if it is lossless, right, then it means that gamma would simply be equal to J beta. So if attenuation is 0, then it means that gamma is equal to J beta. So all we're saying. And it is 0 if the line is lossless. Right? Well, we know that that is not practical, but for our purposes, we're going to make that assumption. Now, we spoke earlier, and in defining our line, we said that Z was the impedance per unit length, and Y was the admittance per unit length. Yes? Z, of course, was on, well, call it the horizontal element, and Y the vertical element. Yes? The horizontal element, as far as we know, would be your inductance. And so Z would be equal to J omega L. And Y would be J omega C. Nothing fancy. All right? Remember now, Y is equal to 1 over ZC. And ZC would be 1 over omega C. All right? More accurate, this is looking at the modulus. So more accurately, it would be minus J omega C. But, you know, no. It is actually J omega C. That's not more accurate. Because if we have the J, it would be minus J XL. Yes? So the minus would give us back the J. Anyway, we don't have time for networks right now. So if we go back to our expressions, Z0, yes, was equal to square root of Z over Y, which gives us root L over C, since the J omega would cancel. So we're left with L over C. And for a lossless line, because the attenuation is 0, yes, we know it's equal to the square root of ZY. That's what we found gamma to be equal to. Yeah?
Sir,
Yes, Mr. Graham.
my mind is racing to try to get everything that you're saying. All right, hold on. Could you link back? Yes, right there.
You have Z0.
Right screen, yes, sir.
You
Go
have
ahead.
Z0. And now we can go back up here. And we have gamma. We found these already.
Yes, sir.
Good. So what I'm doing here, I'm now saying Z, you know, we even go further back. Go back to your diagram. That's your diagram.
All right, sir.
Z and Y, impedance and admittance.
Mm-hmm.
The Z would be based on inductance.
Mm-hmm.
Your Y, capacitance. Remember the pi model? L, C.
Okay.
We don't change anything, you know. So when we come here, all we are doing now is showing the distributed parameters and showing a small section.
Okay.
So Z is based on your inductance,
Mm-hmm.
and Y, your capacitance. We're up to speed now?
Yes, man. We're up to speed now. Proceed,
All right.
sir. Proceed.
So Z0, as we calculated earlier, is equal to the square root of Z over Y. So if I divide these two, I'm going to get the square root of L over C. Because the J omega, will cancel. Because the line is lossless, the attenuation is 0. So if the attenuation is 0, it's also telling us that R is 0, right? So that's what it's also telling us. So gamma, which we found to be equal to zy, if we multiply these, we're going to get j omega squared times LC. When we find the square root, we're going to get j omega square root of LC. Okay, folks? Therefore, it suggests to us that beta, because remember we said that gamma was equal to alpha plus j beta. Yes? So where we just saw that gamma is equal to j omega root LC, then it means that beta is equal to omega times root LC. So I'm using a little dimensional analysis. We have given you the units for beta, which is radians per unit length. All of us know what the unit for omega is, which is radians per second. Yes? So for me to get radians per unit length, then it means that I'm going to be multiplying by second per unit length. We don't know any unit like that. But we know length over time. We don't know time over length, but we know length over time. Length over time is speed. So what this is saying to us is that the square root of LC is equal to 1 over the speed, or the reciprocal of the speed. So coming back to the whole wave analysis, L and C are parameters of our transmission line. It's the inductance and the capacitance of our transmission line. So what we are in effect saying is that the speed at which the signal travels through the line will be dependent on the product of the inductance and the capacitance. Now, immediately, well, let me withdraw that. That should suggest that the speed at which a particular wave or voltage signal is going to travel through an overhead line, well, a line, which we know are all overhead, right? The speed at which it will travel over a line will be different from the speed at which it will travel through the cable. That's how I go. Now you tell me, based on your superior knowledge, if light, we know that light moves through air at a different speed than which it goes through glass, or sound through air and through water. We know all of that. So when that light coming from the air hits that prism that we are there within physics, what happens? Come on, man.
Refraction.
It's separating, sir.
Huh?
It just reflected.
Yeah, refraction.
The refraction occurs.
So you have refraction. That's it.
The
You have some reflection also.
And reflection.
All right, so you're going to have reflection and refraction. And the reason for that is because it moves at different speeds in the different media. The same thing is going to happen when we connect a line and a cable. Because they are different, you're going to have reflection and refraction. And so if we don't consider this, we can end up destroying equipment. Because if it is reflected, it means that you're going to have a wave coming back at you. But while the wave coming back at you, there's one that is still going forward. That's how it goes. So when these two waves meet, what's going to happen? When you have two waves meeting, what's going to happen?
You can superimpose or
Superimpose, so you have what? Talk to me, no, man.
A resultant way.
And the resultant can be what? What going to have on the resultant? The resultant can be what?
The combination of the two waves.
Let me know what a resultant is, Mr. Rose. So let me draw it through the computer.
Either destructive or something, sir.
It's either constructive or
fair?
destructive. So it means that it can get larger or it can get smaller. You with me?
Yes,
sir.
So in terms of your equipment, you might have set up your equipment to handle 138 kilovolts. Bearing in mind, I mean, I am delving a little into it before we actually look at the math, but insulation in electricity is a function of voltage. So the type of insulation you use is dictated by the voltage that you are working with. So if you look on your sheath cable, for example, you will see it marked 500 volts or whatever it is set up for. What they are saying is that this cable must not be used on systems greater than 500 volts. Why? Because the insulation is what dictates that. However, in terms of the size of the conductor, that gives you, or that's a function of the current carrying capacity. So in your power system, the same is true. The next time you drive around, you take a note. You'll see that the insulation used in and around your neighborhood is of a different color from the insulation that may be used down by the Park. Similarly, the insulation color may be different from what you will see going into Hope. Why? Because what you see around the neighborhood is set up to handle 24 kilovolts. What you see at Hope is set up to use or to deal with 69 kV. And what you see down at the Park, yes, is set up to handle up to 138 kV. And insulation is expensive, so you're not going to buy 138 and use it at 24. All right, so I'm saying all of that to say that your system, if we do not take transients into consideration, may result in over voltages, which then produces the flashovers that we mentioned. Because the voltage back on the system, from the line back on the system, would be higher than what you would have set up your system for. All right? Okay, so root LC, 1 over the speed. So the speed mu is equal to 1 over root LC, and that is measured in meters per second. And that is with your inductance and your capacitance in Henry per meter and Farad per meter, respectively. So for your inductance in Henry per meter and your capacitance in Farad per meter, your speed would be in meters per second. All right, so we said earlier that the general expression for our voltage was PE to the gamma X plus QE to the minus gamma X, yes? And we said that P and Q were based on the conditions at either ends of the line. Those values will be given by VI and VR. VI, incident. VR, you reflected. Right? So incident is what you have applied to the line. Reflected is what will be coming back at you. Yes? We'll make some other statements about these two. Yeah? What do we mean by incidental affected? Or let's look at that from a diagrammatic standpoint. Any system, when I energize, all right? So that's my switch, that's my generator. I energize the line, that's my bus bar. Yes, I'm gonna have an incident wave. VI, which is equal to I times Z0, surge impedance of the line. And I'm going to have a reflected wave, which is equal to IR Z0. The negative there really speaks to the direction of travel. Sorry.
All right, so sir, basically, I'm deducing that we're based on everything you have said, you're heading to a fault. I'm seeing that, but what I'm not understanding are
I'm heading to what?
a fault. I'm seeing where there because of how transient. I'm trying to relate the topics over. So I'm saying that oh Lord, I moved my train of thoughts.
You
You
said he was
say
heading
we're
to
heading
a
towards
fault.
a fault?
Yes.
No, not necessarily.
The
Not necessarily. And I said it earlier. I said a transient can, listen, a transient, as we said, is the period between initiation and steady state. That's all that the transient is. That transient can be created by a fault, but it can also be created by normal operation. So the fact that I had some work being done and I de-energize the system in order to get the work done, and I then re-energize the system, I'm gonna have a transient.
Okay.
Because I am turning back on, I'm re-energizing the system.
Okay.
So we're gonna have transient.
So if lightning strike the line, wouldn't that give you a transient as well?
It's a fault, yes. Remember, you know, it's any change, it's initiation of a change. And steady state. Listen, if I have a fault on the system, well, you know, unfortunately, because we're not really doing power systems analysis, but we're doing electrical power systems, which is just, you know, telling us about the system itself, but we're not delving into it. Things will happen to your generators. You may even have a situation where, let us see, you know, give me a big customer, JF Mills. Let us say JF Mills have a problem, or cement company, one of them, anyone have a problem. and they had to shut down. So they came off the grid suddenly. It's going to create havoc for the generators down at Rockfort, which in of itself would represent transient operation.
That means things will be going back to the lines now.
Well, the havoc we're talking about here is that, remember the generator, there's a large amount of, you have momentum, large inertia. And based on the mechanical input to your generator, you can't just change that as quickly as you can turn off a switch. You can open a breaker. And so the generator would overspeed or speed up because you remove that large load. The question is, can it handle that change? Will it handle that change? How do you determine what sort of disturbance it will live up to? So the point we're making today, don't think of transients only be, as you said, leading to a fault. I'm not sure what you mean by leading to a fault, right? But a transient will result because there's a change in the system. So a change is initiated, whether deliberately or otherwise. Some afraid to talk about lightning. I mean, we don't put the system out and invite lightning.
All right, sir.
But it will result in a transient. All right? Okay, so we are saying this will hold true. We have an incident and a reflective. I want to look at the relationship between the voltages and the current. I0 is going to be equal to 1 over Z0. And remember, that's V. We have proven that earlier. Right? And I0 is therefore equal to I incident, because that is VI over Z0. VI over Z0. VR over Z0 gives us the minus IR, okay? And we're noting here, and please put this in red, all right? The negative there and the positive. The positive is just showing increasing X. So it means that we are going away from the source. And for the reflected, it's a decreasing X. So that's how the negative comes into play. Okay. So the voltage with respect to distance and time, yes, will be V incident T minus gamma X plus VR T plus gamma X. And for your current with respect to distance and time, it will be 1 over V0 times your VI. But again, the negative there represents the direction of travel, or the X in terms of reducing X. All right? For your current. So Z0, as we said before, as is your surge impedance. We know that gamma is equal to 1 over the speed. Mu, of course, would be a speed. So that's the fancy theory that we need to talk about. All right? And that's, I mean, I'm not here to quiz you on theory.
Sir,
Yes, Ms. Henry.
for the propagation constant, sir, that symbol there, sir, what is it?
Gamma.
So it was
Gamma. It's capital gamma.
okay, thanks, sir.
All right. So some of the figures that I'm about to use, they are in the the file I put up on Schoology, so you can refer to it. Or, you know, if you wish to draw them, fine, no problem. All right, just excuse me a sec. I've been talking louder than I normally would. So just let me get some water. Just give me a minute. All right, so where do we go from here? Let's do that. Here we have a lossless line of surge impedance Z0 and propagation constant gamma. All right. In a sense, I'm not, you would not be given Z0 per se. What you know would be the characteristics of the line in terms of the inductance per unit length and the capacitance per unit length. And you would have to determine, you know, what gamma and Z0 would be equal to. So if I have an infinite line, of course we know that there is no such. But if I have an infinite line, what we're saying is that when I energize the line, because it is lossless, it means that I will have a voltage E going along the line from 0 to infinity because it's infinitely long. So it's lossless, so the magnitude would not fall. Yep. We're dealing with a normal line, which of course would have losses, then we'd expect that the voltage would be reduced. Okay? So for this, here are the key points we're gonna make. Ready? As I said, these diagrams are in Schoology, so you can access them at a later date. Let's call that figure 1. So for the line shown, this is what I need you all to be taking note of. For that line, the source of amplitude E is applied, then the voltage wave would travel at a speed of 1 over gamma along the line. So E would travel at that speed along the entire length of the line. And that magnitude will not be reduced. So it will remain E for the entire line. As a matter of fact, I don't think I may have said this earlier, but when we showed the first diagram with the elemental section, what you will be seeing is that for each portion of admittance, the voltage would appear. Yeah? So we'd have a voltage from the sending end. Yes, we'd have a voltage at the first admittance. Then we have a voltage at the next. Then you have a voltage at the next because we're having the voltage drops, due to Z. Yes? In a sense, what we are doing is charging those capacitances along the line, which is why in power systems, we usually say that we energize the line or we charge the line, whichever floats your boat. All right? Okay. The corresponding current would be E over Z0. And we, of course, know Z0 is your surge impedance. What are the other points that we can make about what is here? We also note that because the line is infinitely long, then that incident wave would carry on indefinitely. But of course, that is our theory. We don't hang line, for the sake of hanging line. We want to supply loads. So we say now, where we have a point of discontinuity, and what's that point of discontinuity? One, we can reach a load. And that load would be in the form of, based on the fact that we are looking at the transmission level. Yes, that load would be in the form of your substation. We can also connect to another line via the substation again. Yes. So the point of discontinuity can be a load, can be another line, can be a cable, all right? Because if the two lines are dissimilar in terms of their inductance and capacitance per unit length, then that becomes two different surge impedances. So the lines are different. So you then have discontinuity. So in other words, the speed, the propagation speed will be different from line 1 as against line 2. So you'll have reflection and refraction. Okay? So where you have a point of discontinuity, then you'll have a reflected voltage wave. Of course, as you all know, if I'm able to terminate this line in its surge impedance, then the reflection will be 0. All right? But we're going to look at that in a few. How much time do we have? Oh, 5:30. Okay. So this is what we are saying. Here's my junction. That's my point of discontinuity. So you don't have to draw another, well, you can. Yeah, let me leave that. All right. So I have, again, I'm energizing my line. So I close my breaker. I energize the line. I have a surge impedance. It's going through a line of surge impedance Z0. I'll have an incident wave. When it hits the point of discontinuity, I get a reflected wave. But in addition to getting a reflected wave, remember now, not everything will come back to the source. Some will continue. to the load, right? Because that's the purpose of the system. The system is to feed this load. So in standard physics, we would say that that is a refracted wave. For our purpose, we're going to call it the transmission. So we'll have reflection coming back at us, but we'll have transmission continuing. Yes, Mr. Brown.
Yes, sir. Afternoon. At this point, the characteristic impedance for example, the cable or another line after the junction, what part does the characteristic impedance play in the transmission of the signal?
All right, so what we're saying is that, I mean, we're going to do the math in a few. However, if this is a surge impedance of line X, okay? If what is beyond that point has the same surge impedance,
yes,
then we would not get any reflection.
Sure.
So all the voltage that is coming along our line will be seen across the other element. That's what we're saying.
Okay, noted, sir.
But that would be in an ideal world, eh?
True. All right, thank you.
But good question. All right. So based on what we had before, Vn is equal to Z 0 In, and Vr is equal to minus Z 0 Ir. And we have already spoken about this, and you see I'm repeating it, so you know it's important, all right? Okay. So based on that, what we know is that at any point on the line, that's another thing I should have pointed out. At any point on the line, the voltage would just be the sum of the incident and reflected. And we have already established that, you know, we can have constructive or destructive interference. Eh? But what we know is that we're going to add the two voltages at any point of the line, on the line, to get the voltage at that particular point. All right? So coming from the equations that we had earlier, we know the incident is Z0I incident, and VR is equal to minus Z0I reflected. So that's true. So at the point of termination, really at any point, yes, V is equal to V incident plus VR. So it's true along the line, but it is also true at the point where it's terminated. Okay? So I is equal to I incident plus IR. Let's go back and we can see. Oh, I haven't shown it on this one. So that's what we have here. So the voltage at this point, yes, with respect to Earth, would be equal to this. All right, and the current would be equal to the incident plus the reflected. And that's true. I mean, you can only have one current in the system. It's going to be equal to whatever is reflected plus the incident. If it is that the reflected is negative, then it just means that the current flowing into the load is going to be smaller than the incident current. That's all. All right? But what is true is that I is going to be equal to I incident plus I reflected. Doesn't matter how they combine, all we know is that the combination will be seen. All right? It therefore means that I can write a relationship that a relationship between the voltage seen here and of course the currents with respect to the surge impedance and of course the impedance of the load. So I've connected it to a load. What we know is the voltage here, which we have established is that. We also know that the current coming to the load is incident plus reflected. So I can write an expression for this in terms of this. So Brown, your hand still up?
Sorry about that, sir.
All right. So I write that expression. So remember we said V incident plus V reflected would be equal to the current now, which is passing through the load. Yes, here's the current passing through the load. V equal IR. In this case, IZ, sorry. All right. So that's I and that's Z. But we know what V incident and V reflected are equal to in terms of the surge impedance. So I can put that in. And my objective here, students, is to find an expression for the reflected voltage with respect to the incident. So in other words, what fraction of the reflected voltage or what fraction of the incident voltage is reflected? That's what I'm trying to establish. All right, we have this. So we can factorize and rearrange. So the reflected voltage is equal to Z minus Z0 over Z plus Z0 times V incident. And this represents what we call the voltage reflection coefficient. By definition, it is a fraction of the incident voltage that will be reflected. Any questions? All right. Next, looking at the currents. Voltage over impedance, yes. The voltage is given by V incident plus VR. We're dividing that by Z. No, this is Z, which is the impedance in which we have terminated the line. All right? Load impedance that in which a line is terminated. Now we know what Z or VI and VR are equal to with respect to the surge impedance. All right. So this would be VI and VR. Okay. And of course, when we cross multiply, this would give us Z times I, which is I in plus IR. So please take note of the fact that this is Z, but this is Z0. All right. Again, we simplify. Our objective here is to find what the reflected current is, or what portion of the incident current is reflected. So we simplify this. And we get IR to be equal to I times Z0 minus Z over Z0 plus Z. And this is alpha I. All right, so.
Excuse me, sir, for the two equation that you set forward, because in the earlier one, you say a fraction of the incident voltage is reflected. Is it relative in terms of, because earlier we talked about it being superimposed and all of that, but I'm looking at fraction. Is it relative in terms of, because what can more be refracted than what go forward, sir?
Let's look at the equation and you tell me. Because you're subtracting in the numerator. Oh, it must be smaller.
It's smaller, yes, sir, it is. Times.
All right. But based on what we also said, if you terminate it in its characteristic impedance, then the numerator would be 0. So reflection would be 0. So nothing would be reflected.
Okay.
So what you will see here, I mean, I didn't want to get into this, but you see that the numerator for the current reflection coefficient is simply the negative of the voltage reflection coefficient. So it means that alpha V is equal to minus alpha I. So we're gonna call it a day. We're gonna leave it there for today. Let me just get the register. All right. So I want you to take your time, go through what we have done today. We will go through a little exercise next week, which will require you to go through the the notes and have the figures that I already sent you, have them available at the next class. So we will try and make sense of all that we have spoken about this afternoon. All right, let me